So we know how to find the area between the curve and an axis. And we actually just kind of learned how to do it with the y-axis. But we can even go farther and find the area between two separate curves. And we can define these two ways. One, you can do a curve that's a function of x and another function of x. So two functions of x, f of x and g of x. But you can also do functions in y, like f of y and g of y, right? So we can either go vertical with our rectangle. So imagine our rectangle in here. There it is. It has a width that is dx, right? Delta x, but then it turns into dx when you put infinitely many rectangles in there. And it has a height that is, well, equal to something. So let's look at that. Okay, so if this is my upper curve and this is my lower curve, right? And I have limits of integration that are the left and the right. So I have over here on the left side, I have, right over here is the left, that's A. And over here I have B, which is on the right. So when I take my limits of integration, I'm going to go from left to right, right, from A to B. And now my integrand will either be f of x minus g of x, which would actually be the case for this example, because f of x is the upper curve and g of x is the lower curve. Or I could reverse it if g of x is the upper curve. It just depends on which is your upper curve. So in other words, if I'm taking this integral to find the region between two curves, I'm going to go from A to B, and would either be f of x minus g of x or g of x minus f of x. It'll be the upper curve minus the lower curve, whichever one that might be. And then, of course, my dx is that. As a matter of fact, that's what the height is. The height is upper minus lower. And to color code this for you, I should keep my colors consistent. Sorry about that. So my height is upper minus lower, which could be this or it could be this. It just depends. This particular picture is the first one. Okay, now if I'm going left to right for my integral, for my rectangle, and then also my integral, then it works slightly differently, because now my thickness, my width, is dy. C is actually the lower value, lower here, and D is the upper value. So I'm going to pick my lower value here, my upper value here, or the higher number, if you want to think of it that way. And again, it'll be either f of y minus g of y or g of y minus f of y. It just depends on your problem. So you're going to go from C to D, but the width, or excuse me, the height or length is equal to the right curve minus the left curve. Right. So when I go down here, it's either this one or this one, depending on which one's on the right and then which one's on the left. Okay. All right, so they work very similarly, right? But the one major place to make a mistake is in the setup. If you subtract in the wrong order, if you put the wrong one over here or here, if you choose the wrong way, you'll end up with a negative answer. And you should never, 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 never get a negative answer when finding the area for the region between two curves. It should always be positive. Even if it falls below the x-axis, it doesn't matter, because you're finding the region between the curves. So that's fine. In other words, the integrand will always be correct if you write it as the absolute value. So I could say from A to B of the absolute value of f of x minus g of x dx, if I'm going that way, or from C to D of f of y minus g of y. dy. The danger, of course, is what if you mess up this direction? What if you accidentally think you should be integrating with respect to x and you should actually be doing y and vice versa? Well, that's going to be difficult and you'll have to work on that. All right, but we'll work on it with some examples. So let's look at an example here. We want to sketch the region enclosed by the following equations and decide whether to integrate with respect to x or y. So we have to make that decision. Then we're going to draw a typical approximating rectangle, label its height and width, and then calculate the area of the region. Okay, no problem. So we want to look between x equals -1, which is right here. It's a vertical line. And x equals 2, which is right here. And it's between these two curves. So this curve and that curve. And I should label the curves to be smart about it. Okay. All right, so the two curves are f of x, which is 9 minus x squared, because that's a parabola. So even I know that that is f of x. And then g of x is, I don't know, this blue one right here. There we go. Okay, so and I'll highlight that one too. There we go. Okay, and we're going from -1 to 2. We're cutting off right there at 2. Okay, so now I'm going to draw a rectangle. And it's rather obvious here, if these two values are given -1 and 2, that we're going vertical. Like this. Okay, so we need to think about the width of that rectangle and the height. Now the width would be dx, right? Because we made this with respect to x. So when we know that we're going with respect to x, so we've drawn and shaded and all of that stuff. So step 2, we're integrating with respect to x. We know that, and that means that our width will automatically be dx. Okay, so we're drawing a vertical box, a vertical rectangle. Now the length of the thing is the difference between the upper and the lower, right? So it'll be, actually, let me do it this way. Do it in purple. All right, so the length would be the upper, which is the green one, minus the lower, which is the blue one. Where it'll be f of x minus g of x. That's right, there's a subtraction in there. It got weird. There we go. Okay, so now let's use that. Let's find the area. Actually, part 3 was doing the rectangle and all that. This is part 3, doing all the labeling. And if you think you're going to be able to get out of that labeling, you are incorrect, because that's going to be very important to be able to do for some later problems in 6.3 and 6.4 and 6.5 as well. Okay, so we want to find the area here. So I'm going to integrate rather obviously from -1 to 2. I mean, it gave us those specific values. I mean, there's A and there's B, no problem. Now, what I want is length times width. The length is f of x minus g of x, right, which is the upper and the lower. Only for this region. I mean, if you were finding this part over here to be g of x minus f of x, it all depends on which portion we're looking at. And then, of course, of width of our rectangle is dx. All right, lovely. So this is the integral from -1 to 2. F of x is 9 minus x squared minus g of x, which is x plus 1 dx. Let's see, that's the integral from -1 to 2 of 9 minus x squared minus x minus 1 dx, which is the integral from -1 to 2 of 8 minus x squared, which would be 8x minus 1/2 x squared minus 1/3 x cubed, from -1 to 2. And I don't know. I can show all the work. 8 times 2 minus 1/2 times 2 squared minus 1/3 times 2 cubed minus 8 times 1 minus 1/2 times 1 squared minus 1/3 times 1 cubed. And then I will use Desmos, shall I? Seems to make sense. I mean, why do all this by hand if I don't have to? Speaking of which, there's the problem right there. So if I want to do this particular piece, if I just want the math part of it, I could take 8 times 2 times, or minus, it helps if I write this out like this, because then I can copy and paste it for the next portion. All right, so there's that piece, and a fraction, it's 34 over 3. And then if I just copy and paste it into the next one, or I could duplicate if I use the little gearbox up there, then I can change this into a 1 here. Oh, it was -1, sorry. -1, I did in my notes, so I'll have to fix that. So it's -1, -1, and -1. Oh, not -4, -1. There we go. So that was -49 over 6. And I'm sorry, I lost the negative here. I don't know what I was thinking. Negative, negative, negative. And then the numbers again were 34 over 3 minus a -49 over 6. And I can just grab that. 34 over 3 minus -49 over 6. Or you could just say plus 49 over 6, either way. And you get 19.5. Which, I wanted to check myself. Lo and behold, oh, I've already done all this work. Would you believe it? It's right there. It's 19.5. Look at that. Did they give, oh, they gave us units. They said meters, so this would be meters squared.